Okay, thank you. So, yeah, let's just get started. Imagine you wake up one morning as an electric fish, and that the only way you can see the world around you is with your electro senses. And so this morning you want breakfast, or you leave home and you wander around, and one thing that could happen is that you find food right away. And that gives you a sequence of two events separated by one time interval. Another thing that could happen is as you wander around, you find a landmark, and then from this landmark, you find food. And that gives you another kind of sequence, this time with three events separated by uh, two time intervals. So in either of those situations, you'd like to remember where the food is. So what's the best way to encode this sequence information? Well, you can use the cells in this area of the brain called PG, and these neurons respond to new encounters with bursts of spikes. And the intensity of those bursts, so the number of spikes during a burst, depends on the time elapsed between subsequent encounters. So we model this adaptive bursting activity with this resource-based model that has different parameters, such as the recovery time constant. And we can actually show through estimation error analysis that for situation one, where there's only two events to encode, the best way to encode this information is with a homogeneous population of neurons. So with only one recovery time constant, for example. And we can show this for different kinds of distributions for the time interval values. So this raises the question, why do we actually see in measurements in real fish a heterogeneous distribution of adaptive parameters? And so, yeah, if you want to know the answer to that, make sure you stop by my poster session.
Amazing. Thank you so much for keeping beautifully in time. Thank you. You can stop sharing screen. So the next speaker is Pengfei Sun from Imperial College London. Pengfei, please share your slides.
Hi, thanks.
Okay, go ahead.
So we explored heterogeneous delays for efficient computation in low-bit neural networks. We utilize imprecise weights, and we introduced heterogeneous exon delays. We choose exon delays because it's a very parameter efficient solution, because it's just to introduce neural-wise parameters. And in the figure 2, for the SH data set, as you can see, we can get a high efficient solution 1, which just utilize 3 states, positive, negative, and 0 weights with imprecise delays. And if we further increase the delay bits and weight bits, we can get a very high performance for solution 2. And in the right picture, we plot the delay and weight distribution of both solutions. And in the figure 3, we also explore the relationship between the delay and performance for the SHD. If we prune the longest delay associated neurons, it can result in the large drop for the performance. And we also explore the relation between with other temporal parameters like time constant. We use a shared homogeneous time constant. If we gradually increase its value, the mean delays decreased. But there still exist long tail delays, which might suggest that the time constant can absorb some temporal structure maintained by very long-term delays. But long delays are critical because it maintains the long-term information. We also explore the penalty effect, which might suggest that the short-term delays are not that important because it can be compensated by the weights. So by combining all the analysis, we can get an optimal solution. We can get a very high performance, low memory, and very low delay buffers. For both layers, the mean delays are below 15 time steps, and the sparse long tails are below 60 time steps. We would like to suggest temporal heterogeneity is an important principle for efficient computation, especially when task-relevant information is temperature. Thanks.
Okay, wonderful. Let's move on then to the next speaker, Abdelkader Al-Kilani, also from Imperial College London. Yes, I see Abdel. You can share your screen. Okay, go ahead.
Hi, everyone. My name is Abdul Qadir Al-Kalani.
Sorry, just to swap the displays, we're seeing your presenter mode in the upper left corner. Yes.
Yeah, second.
Yes, better. Go ahead.
Yeah, cool. Right. Hello, everyone. My name is Abdul Qadir Al-Kalani, and I'm a first-year PhD student at Imperial College London. I'm in the neural reckoning group supervised by Dr. Dan Goodman. And today I'm going to tell you about our project on simulating neuromodulation using neural networks in spiking models. So in the brain, neuromodulation adjusts neuronal and circuit properties over time, controlling excitability, plasticity, and ultimately behavior. But in current spiking models, parameters are static during runtime, or if they do change, it's mostly through local rules and not through a neural network adjusting them. And in our work, we introduce a modulatory neural network, which dynamically adjusts the neuronal parameters while the main spiking network is running. So here's the model. Inputs are fed into the recurrent spiking network, which produces the outputs, while a modulatory network runs in parallel, tuning the parameters of the primary SNN as it runs. This modulatory network can be rate-based or spiking, and interestingly, this shows that spiking and artificial networks can coexist and cooperate, which was actually the original goal of the project. So the rate of modulation, or how often the parameters are updated, is a tunable hyperparameter, and different tasks prefer different rates. But across all the tested data sets, neuromodulation consistently improved the performance. So here, SHD, SSC, and DVS, we see that these graphs show that across all three data sets, modulated networks outperform static ones, especially when the modulation was happened more frequently. So there was a shorter interval time. And this dynamic tuning also allowed the network to listen in the dips of noise. So when we added sinusoidal noise to speech data, the modulated network maintained higher accuracy and the gap widened as more noise was introduced. So here. So modulation seemed to make the network more noise robust. And how exactly is the modulatory network doing this? Well, you can come to my poster session to find out. Thank you.
Wonderful. Thank you very much, Abdel. Now we are moving on to the next speaker, John Intriago from Universidad de Chile. Please share your slides, John, and go ahead.
Hi there. You listen to me?
Yes, all good. Go ahead.
Okay. This work is titled Exploring Information Constraining Latent Space in Adaptive Spiking Neural Network. And those days, spiking neural network came in family, integrator, resonators. And resonators are really good performance in several tasks, machine learning tasks on classification. And this work is heavily inspired in this network. And the idea is solve first a classification task, the HDA dataset, and containing the space. What does that mean? Mean that the idea is try to uh, align the input space with the hidden space layer and the binary representation through a loss function to try to conserve the information between the input and hidden layer output through information bottleneck principle. The idea here comes from the learning, information bottleneck deep learning. And commonly these methods are used in artificial neural network. We implement in spiking neural network. And the core idea is try to maximize the information between input state and hidden state in order to try to compress information and at the same time holding the result of the capability on a network. And this is the result of spiking hidden per dataset. Here we have the baseline, which is at a leaf, and this is our loss function. And as you can see here, is we are assuming this part, an average adapting this loss function, which is comparing mutual information, increase on average a little bit. But the cool thing here is that when trained with this constraint, the model converges faster than the baseline. And This is at a leaf, this is our model, and this is our finding of this kind of constraining Latin space representation. That's it.
Great, thank you, John. That was very nice. People can follow up for more questions at your poster. So I'm now going to ask Aphrodite Talidou from the University of Calgary to share her slides. Okay, Aphrodite, when you're ready, you can start. It's not full screen. Yeah, perfect.
Okay, good morning everyone from Calgary. My name is Aphrodite Talidou. I'm postdoctoral fellow at the Hotchkiss Brain Institute here at the University of Calgary under the supervision of Dr. Wilton Nicola. In our project, we train rate networks as well as spiking neural networks using the force method. We know that for force method, we typically need chaotic dynamics in order to train the complex temporal patterns, but here we propose that asynchrony is enough to train such networks. And with this, we particularly consider network topologies that look like these rings, okay? This is just a cartoon, and there are thousands of neurons. And here I have included just one example of Lorentz, which is the Lorentz attractor that is trained for both rate network and spiking neural network. For the rate network, we clearly see that after training, the Lorentz trajectories are very close. Sorry, the trajectories are very close to the Lorentz original ones. For the spiking neural network, in the absence of chaos, we still were able to train this Lorentz attractor and have Lorentz-like trajectories. And let me say here that these plots are after training, okay? So not during training, but completely after training. In my poster, I have included other examples as well. And a very important observation that we have for our ring networks, which is that the connections between the neurons all have negative weights, which means that our networks consist of inhibitory interneurons, and so there are biological applications there as well. You're all very welcome to come and discuss this further, and thanks for listening.
Thank you, Aphrodite, for that very nice presentation. So now I ask Gabriel Torre from Universidad de San Andes to share his screen. Okay, Gabriel, we can see the screen. You can start.
Hi, my name is Gabriel Torre. I'm a PhD student at Universidad de Buenos Aires, and I also work at Universidad de San Andrés. And I'm here to talk to you about how I made this little robot walk using spiking neural networks. I created a leak integrate and fire central pattern generator that's wired in such a way that the activity generates cyclic attractors. Here, teal and blue drive brown, that drives orange and pink, that excites gray, that again drives teal and blue. So we get a cyclic pattern. And here, using exactly the same network, we get a different pattern. Then we have a function that is able to detect these two patterns. We have a switch that we can detect, say we want to look at this one or at that one. And this drives dopamine that in turns affect global inhibition. For example, here in the dotted line, we have said we don't want anymore this pattern, we want this one. So dopamine goes down because it's not doing what we want, the pattern we want to look for. The system explores, activity goes up, and if within that chaos we see the pattern we are looking for, then dopamine starts rising and the system freezes in that dynamic attractor. Then we take those activities and use them as triggers to move the legs of the robot using some very standard robotic stuff. And we have a robot that we can tell it, do this type of gait or this one. Here we are asking for bound, then we will ask for walking. We will ask for bound again, and we can on the fly change the gait. What I find interesting of this is we are globally affecting the inhibition levels, but we are getting local patterns. And for more info, please come to my poster.
Okay, thank you, Gabriel. That was very nice. And we have now Julia Gigax from FMI Basel as the next speaker. Okay, Julia, you can share your screen.
Yes. Can you see my slides?
Yes, looks good.
Good. Then, hi everyone. So, for an animal in the wild, a single sensory input might be important for many different things. So, if, for example, this fish now perceives an odor, it might be not only important to find out what this was, like this predator here, but also the location. But how does this these different computational tasks have actually different optimal representations of the sensory input. So how do early sensory areas satisfy all of these different demands on the representation? Well, if we only go for the what, this can be explained by classical attractor models that are basically these excitatory-only assemblies with global inhibition and typically lead to this discrete attractor states. However, if you would want to maintain the continuous information at the same time, you would need a second representation of the input. But the brain might actually be more economical and just form one multi-purpose representation. So co-tuned excitatory inhibitory assemblies, they have recently been shown that they form these neural activity manifolds that are continuous but warped towards certain more like discrete states. And hence they could maybe represent both the continuous and the identity part. Hence, I'm wondering whether excitatory inhibitory assemblies are ideal for efficient multi-purpose representation. Therefore, I've set up this environment with different odors and multiple tasks based on the same input. And I trained recurrent daily and spiking neural networks on all of these tasks to find out whether after learning they form excitatory inhibitory assemblies. And if you want to find out more, please come to my poster.
Great, thank you very much, Julia. Very nice. And now we have the final speaker of the Flash Talk session, Abolfazl Hajiki Far from Shahid Behteshi University. Can you please share your screen? Okay, wonderful. We can see it. Maybe you want to put it in presenter mode just so we can see it, or it's already how you want to show it. Okay.
Can you see it?
No, now we cannot see it anymore. We could see it before.
Right now?
Yeah, perfect. Now we can see it. Okay, go ahead.
Okay, just a minute. Okay. Hi everyone, I'm Alpha Saidifar, and today I briefly talk about energy-based and transformer models for neural circuit modeling. Large language models like GPT-4 have transformed AI by predicting text token by token. They rely on probability distribution over discrete symbols, which works beautifully for language, but not for continuous high-dimensional neural signals like those recorded from real brain circuits, like calcium imaging or other like of invasive neural data. Neural activity is dynamic, multimodal, and uncertain. And when we tokenize it, we lose the temporal and structural richness. That's key to understanding neural computation. that's where energy-based models or EBMs comes in. Instead of predicting tokens, they assign an energy value to every possible state and search for configurations that minimize energy. That is the most consistent state with the data. This idea dates back to Half-Field Network and Boltzmann machines, which you can see here, and recently developed by Jan LeCun, which is known as the godfather of deep learning. Recent advances show that with modern training like counter-ACIV or self-supervised methods, EBMs can model complex continuous dynamics and making them promising for neural circuit modeling. But to model the real brain function, we also need biological structure. Neural computation depends on the motifs like recurrent loops and lateral inhibition and feedback. At larger scale, we see topographic mapping and dimensionality expansion, which is shaping perception and action. If we connect these motifs to AI mechanism, such as linking attention in transformer or attractor dynamic in EBM, we can begin to bridge machine learning and system neuroscience. Thank you for your consideration.